Welcome to Zero. I am Akshat Rathi. This week, cables everywhere. Have you ever thought about how electricity gets from where it's generated to your home or to your office? How, when you flick a switch to turn on the lights, the electricity just works. It's a form of modern day magic. That electricity runs through a series of cables. The ones in your home, running from your bedside electricity socket into your phone, are thin, just a few millimeters thick. The ones connecting your building to a nearby transformer, a little bit thicker. And the ones connecting countries, traveling hundreds of kilometers across the seafloor, are enormous. How big is that cable?
Yeah, diameter-wise, you would say that perhaps it's 25 centimeters in diameter.
So I could literally be hugging a cable.
Absolutely. Both literally and metaphorically. Definitely, yes.
Oh, wow. My guest today is Claes Westerlind, CEO of cable manufacturing company NKT. Headquartered in Denmark and with manufacturing facilities across Europe, NKT is one of a handful of companies that designs and builds these highly sophisticated, high-voltage electricity cables that connect our world. And right now, their products are in huge demand, so much so that a lack of cabling is considered a huge bottleneck to building the clean energy transition. This week on Zero, I go deep with Claes on the cable industry. How are these giant cables made? With so much demand, why are cable manufacturers so hesitant to expand? And is China about to eat everyone's lunch? This is the third episode in the Bottlenecks Series. If you haven't listened to the first two, please check out those episodes on the shortage of transformers holding back electrification and the shortage of skilled workers holding back the energy transition. Claes, welcome to the show.
Thank you.
So NKT makes low, medium, high voltage cables to move electricity, and you've been doing it for more than 100 years. Could you just start by explaining what goes into making these cables and how do those differ based on the voltage?
Yeah, first let me just say I'm pleased to be here today, so very much looking forward to our conversation. And as your question suggests, they are a little bit different, the types of cables that we make. What is common for all of them is that they do transport electrons. They do transport electrons from where they are generated to where they are consumed. But if we start with maybe perhaps the most highest voltages cables that are in essence part of our transmission grids across the globe, they tend to look simple when you look at them. A cable I've come to appreciate and learn over the years that it is significantly more complex than what just meets the eye when you see these cables. Part of the complexity, of course, is that if you look at a very high voltage direct current cable, able to carry roughly 2 gigawatt through 2 pairs of cables, that means that the equivalent of 1 nuclear power reactor is flowing through 1 cable. And while it's doing that, you can also put your hand on the cable. And that has to be a product that can, sustain a lot over the 30 years or 40 years lifetime that these cables are in service for. So how do we then make them? At the center of the cable is the conductor. Conductor is made of metal. It can be of aluminium. It can be of copper. And the role of the conductor is to carry the electrons through that. The conductor you make basically in the same way that you make a rope. So you twist and turn metal wires or profiles together so that they constitute a rope of course, a much finer measure than when you think about an ordinary rope, but yet very similar. On top of the conductor, we place what we call the insulation system. And this is, in the cable world, that's the heart of the cable system. That is the layer in the cable that gives its withstand capability so that you can put your hand outside the cable while a lot of power is flowing inside the cable. Basically, you avoid to get an electrical shock. This is being applied on the conductor for the larger cables in what we call an extrusion tower. So it's typically a very high building. I'm sitting and speaking to you from Karlskrona in Sweden, where we have 3 towers, the highest tower being 200 meters above ground. So the tower that we have here is the second highest building in all Nordics. So that gives you an appreciation. It's not a small building. And the cable goes up into the tower. In the top of the tower, we are dressing it with 3 different layers of insulation. And we do that vertically because Mother Earth otherwise would try to make the cable oval instead of round. And we need to have a perfectly round cable to be able to sustain all the power within. On top of that, and you can hear it is more complex than what meets the eye, we do a process treatment of the cables to get the right properties or residual products out of them. We add sheets that will make them water resistant so that you can lay them in RCs, and we also mechanically armor the cables, so basically putting wires around the cables to make them mechanically robust, both to be handled during installation but also to be resilient when they are at the bottom of our oceans or wherever they are going.
Well, that is a lot of complexity for what looks like a simple idea, just to be able to move electricity through a conductor from one end to the other end. And I want to break down those steps a little bit. So let's do that first and then come to the business side. You said at the core is the conductor, could be copper, could be aluminum, but you also said that it is made like a rope. So it's not a solid piece of metal, it's many wires joined together and twisted like a rope. Why is that the case?
Yeah, typically, you can also have solid conductors, but solid conductors you would have for smaller power rating of cables. And the simple reason is that the mechanical properties of a solid conductor, it becomes very sturdy, very firm, very fixed. So it will become difficult to handle the cable itself with a solid conductor. And that is why you would move to what we call compacted conductors out of wires, or even profiled conductors. And it's basically just a lot of different wires being strung together into one large conductor. So if you look at it, it almost looks like a solid metal surface, but in actual fact it is not. It's comprised out of a couple of different layers of wires or profiles.
And then you said you have to have these cables go in this large 200-meter tower, because if you don't, the coating that you're going to put on, which is the insulation, which is going to make the cable safe, will become oval rather than round. What does that mean?
Yeah, in essence, and of course you can do it in smaller towers, but let's say that you would do it in a horizontal manner. So you spray plastic on, or you squeeze plastic on, and we do it in 3 layers, so it's even more complex than only 1 layer. But for the simplicity reason, if you just spray a layer of plastic, then the gravity of Earth will of course try to pull as much as this can, so that before you get mechanical, sturdy or fixed insulation layer, it will tend to be oval in shape, just like a water drop somehow is also affected by gravity. So while if you do it vertically, and then we heat the cable after it had gotten the plastic around itself, then the material, we call it cross links. So it becomes mechanically fixed. And after that process step, we are then cooling the cable also for a defined period of time. And at the end of that process, then it is mechanically stable. So then you can put the cable horizontally without the cable deforming or changing its shape.
And you talked about making cables for different voltages. You explained, I think, the cable that you make for high voltages. What is the difference with lower voltages? Is it just that layers of insulation are smaller and the cable is smaller? It's just a shrunken version?
Yeah, in essence, I mean, I guess if you oversimplify, you can say yes, but there is also even more simplicity to lower power cables. If you compare these very large cables being able to integrate an offshore wind farm or a nuclear power station or whatever it may be with a cable or what I would call, who comes from the large cable word, a cord, that you have in the walls of your house. That cable will only basically effectively have 2 layers or perhaps 3 layers. It has a conductor in the middle, being a copper conductor, which is solid in its nature, to your earlier point. And then it has its jacket and insulation on top of that, so like a small plastic layer. And then you put 3 or 4 small of these cords together, and then you put a jacket around it. And that will give you your what we call building wire. And of course, the process and speed to make such, and also the inherent allowed variance also in terms of quality, etc., it is much, much higher than when you look at the very high voltage cable. If we go back to the first cable I mentioned, if you have that cable and you get an eyelash, for example, in that critical insulation layer, you will immediately have a breakdown. So then that means that the power of the nuclear reactor will immediately find its way right through the insulation layer and right into the ground, and thereby, maybe putting a city out of its power or, causing a major grid disturbance.
Now, before we go into understanding the business side, there's one other technical aspect of this which most people don't think about, which is our grid works on alternating current, which means the power, sense is actually going back and forth. The voltage is increasing and decreasing, but increasingly we are also using high voltage direct current for transporting electricity very long distances or from offshore onto onshore. And you make cables for both. Can you explain what is the difference between a high voltage AC cable and a high voltage DC cable?
Yeah, from the outset of it, it's quite simple. So a DC cable typically, or a DC cable system, will have two cables. It will have one cable where the current goes in one direction and another cable where the current goes in the other direction. So it is, in essence, only a single phase system, if you will. Whereas an AC cable, it is part of an alternating current system, as you rightfully said. And in modern society, we have a three-phase system, and that's to avoid to be having a ground cable. So our three-phase cable systems, they are basically three cables put into one big cable, if you look at our C cables. There is also other differences in it. So it's a different type of material that you use for the insulation system in an AC cable, respective DC cable system. And DC, by all means and measure, are also more complex cable to manufacture because the field is constant over time. So you always only have a plus and a minus, and it will never vary over time. Whereas in an AC cable, as you said, 50 times per second, it varies all the time. And that also has a bearing when it comes to fields building up inside the cable system. So if you have an impurity, as an example, in a DC cable system, the effect of that impurity will increase over time because the field is constant. While in the AC cable, you may get away with a little bit more impurities because of the field is always alternating. So going up, going down, going up and going down. You're charging and decharging the cable.
So coming to the business side then, how are you seeing the field evolve when it comes to high voltage AC versus high voltage DC?
The field that we are active within is, of course, a fairly conservative field. So the field of power transmission and just the whole grid in society is a conservative field. AC has been with us for more than 100 years or around about that. The DC technology as such was in fact invented by NKT, or the legacy parts of NKT, back in 1954. Was the first DC cable. Then it was with paper as insulation system drained in oil. And we claim our first reference, which we are, of course, super proud of, to the island of Gotland, which is in Sweden, and to the mainland. Later on, in the end of the 90s, we also invented the XLPE, so the plastically insulated DC cables. And ironically, again, we had the first reference on the island of Gotland with that. But that's just to give you that both technologies have been existing for a long time. One for about 100 years and the other one for about 70 years. Yet the big shift in society, where DC has really become much, much more prevalent in terms of use, has only come, I would argue, perhaps in the last 5 to 10 years. So it has been increasing over time, but the massive volume applications of the HVDC cables have really started to kick off from 2015 and onwards. And today, if you look at the big project masses which are being awarded, I would say that 80 to 90% are based on HVDC technology as opposed to AC.
And why is that? Why is it that DC is getting an upper hand now and is the area of rapid growth?
There are a couple of different factors that contribute to this change. One is, of course, the inherent, not issue, but the inherent disadvantage when it comes to power and length of transfer capability with AC. So an AC cable, as the current is going back and forth, and the cable as such is like a capacitor, almost like a battery. So in addition to transporting electrons from one side to the other, or transporting power from one side to the other, you also have to charge and discharge the cable all the time. And that means that if you have a very long AC cable, you have to do a lot of charging. And you're ending up just charging and discharging the cable instead of actually transporting electricity from one end to the other. And that puts a physical limit for how long distance you can use AC cables for. And everything depends on the power rating, etc. But you can think about around 100 kilometers if you want to do large-scale power transfer. That's what you can do with AC cables. Everything above that, or with a very much higher power rating, then you need to go DC, because there you don't have to charge and decharge. And on top of that, DC also will offer you significant less losses. It's also more advantageous in the grid because you will also have an inherent capability to control the power flow much, much better, to do emergency support if the grids are in a constrained situation. You can even, with DC systems today, do islanding, or what we call black start, to start up a grid that is completely dead or that has suffered a massive failure through these DC cables and the DC converter stations. And last but not least, of course, the other angle which is also contributing to this major change is just also the fact that the energy transition for the last 10 years has now really, really taken off. While this has been a niche industry that a few of us have really been in love with, I think now the realization has come by society in general and by the world in general how fundamental electrons are for our modern way to sustain life. And us making these systems more resilient, us also taking care of our climate and making sure that we will have also a world to hand over to our kids, has put much more focus on both solar power, offshore wind power, energy trading between countries as well, and that also has increased the demand. And then the last part, which I think personally is quite sad, but also the recent amount of conflicts in the world have also raised the awareness around security around these kind of grids. And of course, with that, also putting cables instead of overhead lines makes you also more resilient towards potential easy tampering or attacks, etc. But also just that hardening of the grid and making the grid more resilient through more investments in the grid is very, very important these days, also considering the security situation.
We'll be back with more of my conversation with Claes Westerlind, CEO of NKT, after this short break. And hey, if you're enjoying this episode, please take a moment to rate and review the show on Apple Podcasts and Spotify. Your feedback really matters and helps new listeners discover the show. Thank you. You also build projects that are on the ground and under the sea.
Yes.
Is there a difference between the cables that go on the ground versus under the sea, and what is the difference?
Yeah, there are a couple of important differences. What is very specific for a cable that is to be put under the sea is the fact that it will be submerged and exercised to high pressure from a water perspective. So with that, it is very critical that the conductor is watertight from a longitudinal perspective, so that if a cable would be torn by an anchor or physically tampered with, then you don't want the water to ingress alongside the cable to destroy large part of the cable. So that's one aspect. The other aspect is that it's very critical that it's also watertight from a radial perspective, that water cannot get into the cable from the surface. And then lastly, from a physical integrity perspective, a cable that needs to be installed below seabed has to be physically more resilient than a cable that to be installed in land for many different reasons. But the obvious one is, of course, if you are to hang a cable from a ship 100 meters down to the sea bottom, or why not 600 meters or 1,000 meters or even over and beyond, then the cable needs to be able to sustain its own weight down there. You will also trench the cable, so to bury the cable underneath the seabed. And these trenchers, they would look like, for a normal person, like a monster, like a sea monster, like a big tank that runs on top of the cable on the sea bottom floor. And the cable, of course, has to be also sustained to be handled and buried underneath the seabed. So I think these are the typical differences. From a manufacturing perspective, you also manufacture them in much, much longer lengths. So a land cable, there you're limited by also transportation onshore. So you cannot take a drum that weighs 5,000 tons on a normal road. There is no truck that can carry it. There is no road that can carry it. So typically a normal cable run will entail about a kilometer of cable and perhaps weigh everything between 50 and I think our heaviest drums are up towards 100 tons. But that's what the limit is. If you look on sea cables, on the other hand, they are being spooled from the factory directly onto one of our cable lay vessels. And there you can load 10,000 tons of cables in one go on a vessel, or like our new vessel that we are now manufacturing, she will be able to carry 23,000 tons of cables in one go, which is very different, of course, to 50 to 100 tons.
And that's why you and your competitors like Nexans, Prysmian, these companies build these manufacturing facilities, these huge towers close to deep water ports. So you're able to make the cable and directly load it onto a ship. But talk me through the cost now, because obviously the cable going under the sea needs to have all these extra properties and that requires extra effort, but then they're easier in a way to move and then to deploy because you're not having to deal with the challenges that come with land deployment. So on a per kilometer basis, how much does it cost to lay down a undersea high voltage DC cable versus an ground high voltage DC cable?
It's a good question. The lawyers would always tell you it depends, so that they cannot give you a straight answer. And I'm afraid I would have to resort to the same kind of answer here. And the reason is, of course, that the designs of these cables will always be different from case to case. But what you have to keep in mind for onshore cables and offshore cables, they are solving a completely different task. So a sea cable, it's solving a task that a land cable cannot solve. So that's why it's difficult to compare them. It's like comparing the task of a normal car with a case of maybe a truck. They are solving two different tasks. I think what you could compare is, of course, onshore cables versus overhead lines, because they are solving a similar task and there are differences into that. But when it comes to a sea cable, there just isn't any other solution for it. Now, that being said, a sea cable is obviously more expensive than a land cable. That's clear, but it's not significantly more expensive. So it's not 3 times more expensive or something like this. And this goes to the fact that the conductor and copper is something which is perhaps the most expensive and precious part in a cable as such. And if you make the conductor the same, the majority of the cost base is the same. And then, of course, there are layers that you need to add on the sea cable, such as steel armoring versus just a plastic jacket on an onshore cable where the costs are pretty different. It's not fair to compare them just like by like because they're solving different problems.
But one thing you can do is put a dollar number on it, and roughly $1 million a kilometer is a number that gets quoted quite a bit when it comes to having high voltage DC cables being deployed. Is that a good range, even if we don't have exact figures?
Yeah, I think, the numbers you find out there, I think you can use them and, as some sort of an approximation. I would be careful, knowing a little bit about the industry, to use it to provide some sort of an exact indication of what it will cost to solve a certain problem.
Is there a range that you would advise to somebody who's considering a project?
No, I would say that I think that's also a part of this industry, like standardization. You could think about, why don't we standardize cables to get exactly what the question that you ask here? So what's the cost per kilometers? Let's make it simple. But the reason is that it does make sense to do it is, of course, if you can save just 200 grams of copper for every meter of cable, and then you multiply that by 700 kilometer, or, connecting Singapore to Australia, multiply it by 3,500 kilometers, it's always worth it. So that's why this industry, it's all about customization. Every cable we make from a high voltage perspective is purpose designed, purpose tested, purpose built to solve exactly that job, because the amount of megawatts to be transferred are different, but also the soil compositions are different. The landing points to onshore is different, and it all speaks into the thermal properties and just the power ratings being different, and therefore the cost of the system will become very, very different.
But then this is creating a bottleneck in electrification, right? We've heard from customers that being able to get cables for these projects is a hard challenge. Many of these factories have been booked out for years altogether to be able to build these cables for those specific applications. So how do you resolve that bottleneck? How do you scale up this industry if you're going to stick with having these custom-built cables?
Yeah, I think this is an excellent question. And it's a question also that I've been privileged to be asked by member states of the EU, also by the EU Commission. And there is a lot of discussions and debates also with Europe Cable, who is a cable association where we organize ourselves. And I think we have a responsibility as the industry to increase capacity to meet the rising demand. If you look at IEA and what they are forecasting between now and 2040, to be able to fulfill the visions or the political targets and ambitions when it comes to clean energy or just energy society in general, and also to refurbish whatever needs to be refurbished in the existing grid. IEA estimates that we need to build an equivalent of 80 million of kilometers of grid infrastructure between now and 2040. Now, how much is 80 million kilometers? That's basically the equivalent of the entire existing grid. That we need to build in 15 years, and that's equivalent to what we have built in 100 years. So I agree to your point that the need, the demand of grid infrastructure is massive. What have we then done as an industry? I can say what we have done as a company, just taking the last 2 years that I've been privileged to be the CEO of NKT of, we have committed and launched investment equivalent to 1.8 billion euros into extending our capacity. This is extending our capacity for high voltage DC cables. It's extending our capacity for high voltage AC cables, for medium voltage cables. So it's across the span. The industry in Europe, when it comes to high voltage cables, have announced investments for roughly about 4 billion euros. So to increase the European capacity to sustain and increase the demand as such. So I think in our opinion, we have made significant investment from 2020 to date, and we are still on that investment journey. Now, we have been able to do that because of society has also taken a step forward with the transmission system operators in Europe, backed by the regulators, also being able to give us a better predictability in the demand needed going forward. Because, of course, as you can appreciate, for a company like us to do investments in the realm of 1 or 2 billion euros, it's a massive commitment. It's a massive amount of money that we are spending, but it's also a massive amount of demand that is needed for this investment to actually make financially sense over the next, not 5 years, not 10 years, but over the next 20 to 30 years. So we have gotten better visibility. We have gotten some larger frame volumes. And I think for us to be able to sustain these investments, or maybe even to make even further investments, this is exactly what we need. A predictable and safe and sound demand in Europe for these kind of products and system. Because the industry has also learned more than what we wanted to about a decade ago when we did make investments, but the demand never came. And expensive as these investments are, it becomes very, very painful then when you are not able to actually produce cables in them.
But this is something that comes up again and again with different types of device makers when it comes to electrification. We've written about a shortage of transformers in especially Europe and America, and it's the same point that manufacturers raise, which is we see there is demand, but we don't know if there is guaranteed demand for us to be able to make the investment. How can both things be true? Because if you can see the demand, how much more guarantee do you need to be able to make the investments?
I think for us, as I said, we made a learning 10, 15 years ago where we did make investments based on the anticipation of demand. And since the demand didn't come, we had a utilization problem, which was a very expensive learning for the industry. But I think I want to give credit. I want to give credit to the member states, at least some of them. I want to give credit to some of the TSOs who have actually dared, backed by the regulator, to make anticipatory investments. So to make commitments to companies like NKT, we will buy cables from you. We don't know exactly for what project, exactly what design, but we will buy projects over the course of maybe 5 years or 10 years. And that gives us enough comfort to dare to take a step forward and also take a risk then. So I think that part of anticipatory investments to make commitments that we will use roughly this much capacity for the next 10 years. That gives us enough. And of course, going back to IEA, from a global perspective, we all know it has to be done. And of course, when it comes to grid infrastructure and generation in general, these are large investments. They are very expensive investments. So also the governments have to have a part in also enabling these anticipatory investments and making it possible for the TSOs to actually carry forward with them.
So we are starting to see investments from cable makers, including yourself, but we are seeing Japanese cable makers coming into Europe. We are seeing South Korean cable makers going into the US. The country that has deployed the most amount of high voltage DC cable is China. Are you worried that Europe and the US are losing the ability, the competitive edge to China when it comes to electrification in general?
I would maybe nuance the statement. I think maybe China has launched or built the most amount of HVDC line kilometers potentially, but not necessarily cables, so insulated cable systems. Am I worried in the way that we in the Western world have interacted with China in the past with respect to technology ownership, with respect to allowing them to act freely in our markets while we have been locked out of theirs, with respect to them being allowed to tender and win and execute projects, which are obvious on unreasonable price and cost levels. So hence, with the risk of being subsidized, yes. I think the Western world and Europe in particular, we have been a little bit too naive in the past around this topic. And that, of course, has also then allowed them to gain quite a bit of ground. I would not say that from a HVDC cable perspective, they are close to where we are. But then if I want to turn a little bit positive, I think if we have learned anything now for the last 1-2 years, under very tragic circumstances, is the fact that strategic autonomy is very important. It's very important when it comes to the core parts and the fundamental parts of your society, where the grid backbone is one. And we talked earlier about electrons, meaning for our modern way of life, etc. And there I see a very different sentiment today in Europe, and I would imagine just the same without being an expert on the US, with respect to how much do we want to make ourselves dependent on foreign states very, very far away for the most noble and the spinal and backbone parts of our society, being the backbone grid. Because things can happen. Whom was your friend yesterday is not necessarily your friend today. And you just need to make sure that we can feed ourselves, that we can have heating at home, etc. So I think there has also been a little bit of change in insight and reflection.
Can you give examples of projects that you are proud of and perhaps projects that you lost to a Chinese competitor?
Happily, on the HVDC side, we haven't lost any projects to them because they are simply not there from a technical perspective where we are. So I think in that high end of the product range, they are not present. We have seen from a distance where they have won AC cables, on 155 kV, so much, much more standardized technology levels. And there they have shown extreme aggressiveness in terms of pricing. And it is for some, and of course, maybe not in the opinion of a court, but I think in the opinion of myself and many of our competitors, it's obvious that price dumping is being used as one of the levers to really get in and buy your way into a market. But luckily, we haven't met them head on in these very, very noble high-end products, partly because they're not there technically, but partly because also slowly insight is actually striking society that we have to think twice before we put this very critical infrastructure in the hands of foreign states far away.
And what are the projects that you are very proud of?
Here you can keep me going for a long time, I have to say. Right now, NKT is installing cables in the United States of America, coupling Canada down to the city center of New York. So through Lake Champlain, through the Hudson River, through the Harlem River, and the cable is terminating in Astoria, right on the other side from Manhattan. This is a cable system that will carry more than the equivalent of a nuclear reactor of clean hydropower coming from Canada feeding the city center of New York, a cable that will turn on and a system that will be used starting next year. So 20% of New York City's power consumption will come through this cable from Canada. And this is through the hands of the technology developed by NKT and produced and nurtured, engineered and tested in Karlskrona, a very small city in Sweden. That's something that we are immensely proud of.
But these days, you can't get away from geopolitics. There was a risk at one point when the trade war was heating up between the US and Canada, where Donald Trump was demanding that Canada become the 51st state, that Doug Ford, who's the Premier of Ontario, said, we will stop sending you power from Canada if you do not back down. Not to stick to that specific example because things have sort of resolved for now, but in general, with the work that you're doing where there'll be cross-border transport of electricity in increasing amounts, how do you think about the geopolitics of energy transport, specifically when it comes to electricity?
I think it's a very good reflection. And it's, of course, something that will impact a company like NKT. It will impact the world, etc. And let me start by saying that conflicts and trade barriers, it's not good for business, just in general, period. That applies to all companies and all countries. Now, with that said, we are a non-political organization. Of course, also we are a humble technology provider, if you allow the expression. But I would also say that cross-border electricity trading and just being interconnected from a grid perspective, it's just from a physics perspective necessary for the grid to be able to operate in a stable manner. And physics maybe is one of the few things that even trumps politics in a sort of way. Now, I think one of the big paradox in our industry is the fact that energy systems are designed, constructed, and operated with decades in mind from an horizon perspective. Politicians, on the other hand, are elected on a 4-year term basis. And of course, they have to gather votes, they have to get re-elected, and they have to do what's right, during, with the winds that are in force at that moment in time. And I think this paradox between the two is a difficult one. And I, sadly also think that that's why sometimes we're also not making the best decisions for example, for a specific discipline like the energy system or, how should we operate the world in 5, 10, 15 years, simply because that does not get you votes. And I think there is no way around this paradox, but I would just, again, from a humble technology provider perspective, of course, we see that when it comes to energy policy, if there was one point which deserves, bipartisan agreements, or like in Sweden, cutting across the different blocks, and the same thing in Europe, I think it really is the energy system, because there you need to have the long-term strategies in mind when you're making the decisions. But to your point, is there a risk in this industry because of political taking decision left and right, changing, rolling back or rolling forward? I don't think I can be ignorant to say that there is not. But I think on the long term, medium to long term, I'm less worried. The fundamentals of electrons as a way to consume energy, the fundamentals of electrons as a way to transport energy is there. So in the medium to long term, sadly, with the impact on climate that we are having on this planet, I think we feel that we are in a robust industry and we feel strong with the portfolio and the capabilities we have.
Well, the robust growth in your stock price speaks to that point. Thank you, Claes.
Thank you so much.
I'm now speaking with Will Mathis, my colleague here in London, and the reporter who worked on the story that told us about the shortage of cables and how it became a bottleneck. Hi, Will.
Hi, Akshat. Thanks.
You've spoken to Claes in the past. You also went and saw one of these massive towers where these cables are manufactured. But one thing that I am still puzzled by is if there's such a demand for these cables and these companies are minting money, why is it that they are not able to resolve these bottlenecks more quickly?
Well, one reason is just that it's very hard to get into this business. If NKT, Nexans, Prysmian, some of the other Asian suppliers that know how to make these cables don't want to massively scale up, then it's hard for someone else to get into the business and start doing it. It's a deep moat as people say, that it's hard for new companies to start building HVDC cables. These towers, they're weird structures. And if you're some other business who's never done that before, you're going to think twice before deciding to build one. And even if you could find a location and find the materials, it's just going to be hard to do. So these companies are investing in new capacity, but they are doing so very carefully. And they want to make sure that every dollar they spend, that they're going to be able to profit from for a long time to come.
But there's a risk with this, which is if it's a big moat and you have these limited number of companies making those cables, they can get into price fixing, which they have done in the past and have been caught and have been fined as a result. Talk us through why that scandal happened in the first place and what could be done to ensure it doesn't happen again.
Yeah, this is something that really surprised me when I was researching the cable industry, that going back as far as 1901, there is documented collusion among cabling companies in Germany. That behavior basically continued up until pretty close to the present day. Back in 2014, the European Union fined all the big cabling companies for collusion. And I read through those documents, and they're, would go around the world and stay at hotels and talk together. And they basically say, okay, you Europeans, you stay in your market, and we Asians will go in our market. And if they got a request for proposals, then they would let each other know and make sure that the right bidder won the contract. And they've been fined. And today they would say that, that's all in the past. And I think if you look there, there's no evidence that it's still going on. But if you look at it, there's kind of no reason to continue colluding. There is so much demand and constricted supply. So, one of the CEOs I spoke to for the story asked him, what do you think of competition? And he said to me, everyone is behaving. So if everyone is behaving, everyone is trying to keep prices at a good level for everyone else. There's not so much expansion of supply, then there's really wouldn't be a need to collude, even if they wanted to take that risk again.
Thank you, Will. And please do check out the story that Will has written. We'll link it in the show notes.
Thanks, Akshat.
Thank you for listening to Zero. This is the third and for now, the final episode in the Bottlenecks series. Let us know what you think of the series and if you'd like us to cover more of these bottlenecks. Please also take a moment to rate and review the show on Apple Podcasts and Spotify. Share this episode with a friend or with your local electrician. And now for the sound of the week. That was the sound of a nuclear reactor starting up and producing what is called Cherenkov radiation. This episode was produced by Oscar Boyd. Bloomberg's head of podcast is Sage Bauman, and head of talk is Brendan Newnham. Our theme music is composed by Wonderly. Special thanks to Will Mathis, Eamon Farhat, Eleanor Harrison Dengate, Samar Sadi, Moses Andim, and Siobhan Wagner. I'm Akshat Rathi, back soon.